And I'm your host, Dr. Matthew Richardson, and today, welcome to another stream of CosmoQuest Astro 101. All right, guys. So, we're going to pick up our discussion um, that we started during last stream talking about the fate of the universe. So, just to kind of recap what we discussed in the previous stream, I kind of wish I had a chance to put this up on the topic slide, but we talked about the geometry of the universe. And basically, there's three different types of geometries, those being an open, a flat, and a closed universe. And those geometries are basically determined by the density of our universe. More specifically, hey Larry, more specifically, the critical density of our universe, which is a theoretical calculation which basically indicates or serves as like a threshold for being able to determine what sort of geometry our universe will be in. Where if our actual density of our universe is equal to this critical density, we will live in a flat universe. If the actual density of our universe is greater than the critical density, our universe will be closed or spherical in shape. And if the actual density is less than the critical density, then we'll live in an open universe, which will have more of a hyperbolic geometry. So the reason why I started off with these particular geometries, talking about these geometries of our universe, is because ultimately, depending on the geometry we live in, will ultimately determine exactly what sort of fate that we're accessible to. So on the topic screen for today, I'm showing some scenarios or some theories as to what will happen in the future of our universe, much far in time from now. We're talking somewhere in the order of like trillions of years from now, so far away from us. But I think that the image that I found here kind of encompasses many of the theories or the more popular theories as to what would happen. And so I'm just going to slowly walk through each one of them. And then at the end of all of this, I did prepare a quick calculation related to the fate of our universe, and figured I would present that, and we can have a discussion on that as well as what I'm getting ready to talk about right now. So let me quickly actually pop out the chat because I want to be able to see comments as I move through the discussions for today. So let's do that. All right. So I'm going to start off with the one that's actually the most scariest to me, which is the Big Crunch. In fact, I believe in the last stream, someone mentioned some of these possible fates, and I believe this was one of the ones that was mentioned. And the Big Crunch is basically the idea that, and of course, with all these scenarios, we have our Big Bang. Um, we are here today, and trillions of years from now, we're going to end up in one of these fates. Now, with the Big Crunch, though, the situation is, as we see here in our diagram, the universe starts with a Big Bang, it expands to the universe we see today. At some point, the expansion will stop, and then the universe will begin to contract onto itself. And basically, what's happening here is that gravity is now winning and causing everything to kind of come back together. And so I'm seeing a question here from Hanny. If the universe had the correct shape for a Big Crunch, would dark energy still be a factor? So in this situation, that would, and given that we believe that dark energy is kind of a force that counteracts gravity, the idea here would be that gravity would have to win in the long run, um, and dark energy would have to lessen in order for this to be true. Now, the situation is this though: if dark energy is large enough, though, even how do I want to put this? It is possible for this to not happen. Well, actually, before I jump ahead of myself on that, I want to go back and relate this to the geometries that we were talking about. So with the Big Crunch, the geometry that would need to be the case for the Big Crunch would have to be a closed universe. Our universe would have to be spherical in shape, meaning that the actual density of our universe would have to be greater than the critical density. Um, but the interesting thing about all of this, and I'm happy that Handy brought that up, it would be that if the cosmological constant, the the term that's tied to our dark energy, if it's large enough, we could still have a closed universe, but still have a situation where we don't end with the Big Crunch. So I found that to be very interesting, actually. So yeah, so Larry brings up the fact that that the idea behind the Big Crunch is also, I can't remember exactly what the name of it is, or the Big Bounce, I think that's what it's called. But basically, the idea that Larry's bringing up there is that the universe can go through these episodes of going through big bangs and then big crunches, and repeating this process over and over and over again in a oscillatory manner. And so that's an interesting concept that's tied to the Big Crunch. And so at the current moment, what Larry is stating is right. Like dark energy is considered to be roughly, I think, about 76% of the composition of our universe. And so Adam brings up a question: could the curvature appear to be close to zero? And basically, what Adam is saying here is, if we have a curvature of zero for the universe, that means that we're basically in the scenario of having a flat universe. Um, ah, so typically, right, because we aren't able to see the entire universe, right? Our limit to how far we're able to observe things is based on it's basically based on the amount of time it takes for light to get from that thing to us. So we're only able to actually observe what's known as the observable universe. Um, and I guess our hopes would have to be that the observations that we're currently making from the observable universe would be true for the overall universe, which includes the part of the universe that we're unable to see. But that was one of the particular things I wanted to talk about today, was the Big Crunch, and how that ties into the geometry that we were talking about in our last stream. And so, rising from its own ashes, the Phoenix universe. Um, and so the next thing I wanted to talk about was this concept of the Big Freeze. And so basically, in this scenario, tying it all back to the geometry that we talked about in our last stream, the Big Freeze corresponds to a universe that is either in the state of being open or flat. Um, and the case would have to be that we have to be an expanding universe. The idea here is that basically the matter distribution gets such that it spreads out so much that we get to a scenario of where it just simply gets colder and colder and colder over time. Just like how at the beginning of our universe it was very hot, and today the overall universe's thermal temperature is roughly somewhere around 2.7 Kelvin. And so the idea is that the universe will continue to keep expanding, and as it continues to expand, the overall temperature of the universe will also begin to get colder and colder, to the point where we get to the point where it's just extra cold, absolute zero, actually, if I'm remembering this correctly. And then I'm seeing also in this particular diagram that there's this other concept called the Big Rip. And to be very honest with you guys, I know very very little about this particular concept, but since it's in there, I'm gonna try to remember what I can about it. I think it has something to do with the fact that eventually everything will break apart at all scales. The exact reason as to why they break apart, I think it has something to do with dark energy. As of right now, we know that dark energy is causing expansion of expansion of mass on a much, much larger scale. But I think in this situation, I think it has something to do with some form of dark energy, um, being able to act on even the smallest scales. So, Hanny, it depends on what you define as a nice temperature. So, if I'm remembering correctly, I think the relationship between time and temperature is that it's inversely proportional to one another. Um, so another way of saying that was that if you take the amount of time that's passed, that amount of time has to be equal to some factor times one over the temperature at which the universe is at. And so I guess yeah, I guess it depends on what you determine to be a nice temperature. If you're talking about room temperature, in units of Kelvin, which I think is like around, and I could totally get this wrong. I think it's around 300 Kelvin. I'm not too sure, but if you're asking for when the universe's temperature was around 300 Kelvin, there's some equations that would definitely assist in solving that. Off the top of my head, I can't remember what that factor would be. I guess it would be something like the temperature is equal to that factor times one over time. So maybe you can solve for the time, given that you know the temperature and that factor that would help you do the conversion. Yeah, the big rip. Thank you, Larry. That's actually a pretty good explanation of what happens with it. And again, I'm thinking this is the situation. I do remember that basically everything rips apart, and I think this has something to do with dark energy being able to act on mass at much smaller and smaller scales over time. Okay, so that's for the most part. That's what I wanted to discuss with this diagram that we have here in front of us. Um, well, yeah, things are cold now. But things are fairly cold now. But I think the situation is that, or am I getting things mixed up? Because there's another concept with heat death. But I think that's it's related, but it's not exactly the same. I do know that with the big freeze, over time, we have an expanding universe. As it expands, things get colder and colder. Um, but it's a great question here that you bring up as to why it gets colder and colder. Maybe it might just be that as so galaxies are far more spaced apart. Interactions between with acting within the galaxies. Maybe it's just that as the galaxies themselves evolve, you get to a point where if it's getting colder and colder, that would have to imply that you're getting stars that are getting colder and colder. So you're not going to be getting the big bright hot stars. But yeah, it's a great question actually that you bring up there. And off the top of my head, I can't really think it would have to be that things are occurring within the galaxies themselves that's causing the galaxies to get colder. And the only thing I could think about with the galaxies getting colder would have to be that you're losing hotter and hotter stars. So yeah, heat death. You're right. Heat death is basically when the universe as a whole has reached maximum entropy, which corresponds to the universe basically being in thermal equilibrium. And like you said, no more work can be done because you can't have a transfer of heat from one place to another. But I'm definitely gonna keep looking at your comments here and questions. Um, but I want to go ahead and start presenting the problem that I worked through. And really, it was this problem that kind of inspired me to want to talk about this. And so let me see if I can quickly bring it up. Just for a quick second, guys, and I apologize for this because I didn't have enough. Well, I had enough time, but I didn't get around to actually uploading this sooner. But I should be able to quickly upload it now. Let's see. All right. And so some time ago, I was trying to determine exactly what sort of topic I wanted to talk about for the Astro 101 stream. And it was a question I ran across in my physics book that I used in undergrad. And I've slightly modified the problem, the question for the problem. But nevertheless, we can go ahead and have a good discussion about it. And so basically, the problem was all about being able to calculate the neutrino rest mass, taking into consideration this concept of the critical density and how it ties into the shape of the universe and ultimately its fate as far as the topics we just talked about a few minutes ago. So so basically, the idea the way in which I changed the question was basically that I wanted to estimate what the neutrino rest mass would be um, if or what would it have to be in order for it to equal for the critical density, or in order for the density or the mass density of neutrinos to equal the critical density of the universe. And with that, of course, I have a few assumptions about the number density of neutrinos, which I think is actually this particular value I grabbed online for the number density of neutrinos. And so let's not assume that, but that's an actual number that I grabbed from online. And so I wanted to start off with the equation that we kind of talked about in our last stream. And let me make sure I have comments up here because I'm pretty sure that I don't want to miss the comments. So, Hanny, the critical density of the universe is essentially the density that would be required to have a flat universe. It's a theoretical value. So it's not the actual wanted to have a flat universe. If the actual density of the universe is greater than this critical density, then our universe will be spherical or closed in geometry. And if the actual density of the universe is less than the critical density, then we'd have an open universe. And basically, these geometries are linked to the fates that we just talked about. For example, the Big Crunch, which is going to be linked to having a closed or spherical geometry for our universe, and then the Big Freeze, which would be more so related to having either a flat or an open universe. Oh, my sound is going in and out. The mic is experiencing a big crunch. I apologize. That's weird. You know what? Actually, that might be because of my hands. I keep putting my hands on the side of my laptop, and I think I might be covering the region of the laptop where sound is input. So I will avoid doing that. I apologize. Is it good now? All right. So this density is not the density the universe would have to have in order for the entire thing, that is the entire universe, to be a black hole. It's just basically that density that basically defines how we can see or how we can determine the geometry of our universe. All right. So in our last stream, we talked about this about this particular variable called the total density parameter, omega. And so what I'm showing here, let's make sure that you guys can see everything clearly. Yes, good. Probably going to zoom in a little bit more just to kind of see this a little bit better. All right. So this total density parameter is ultimately what it will help us determine the geometry of our universe. And so I put here as a note, and I'll scroll down right here. If you can kind of see at the very bottom of the screen, there's a note that says omega sub x is equal to rho sub x divided by essentially the critical density. Now, the key thing here is that with the total density parameter, it has no subscript because it's the total density. However, it does take on a similar form that we see here in the note, in that instead of it being rho sub x, for the total density parameter, the rho is just simply the total density of the universe. But the key thing that we noted here, though, in the last stream was that the total density parameter, or another way of putting it, the total density of the universe, is dependent upon a few other factors. Those factors being in the slide that I was showing in the last stream, it was denoted as omega sub m plus omega sub rel or relativistic, excuse me, plus omega sub lambda, where these particular three terms that are shown on the right hand side of the first equation I'm showing here, first term corresponding to the matter of the universe, which decomposes into being basically a composition of the dark matter content of our universe and the baryonic matter of our universe. As for the relativistic omega term, this corresponds to what we consider to be the relativistically moving particles in our universe. So that breaks down to being the neutrinos, which actually physically have mass, and the photons, which of course don't have mass, but they do have a mass equivalence due to the fact that they have momentum. And then lastly, there is this omega lambda term, which corresponds to the mass density, or another way of putting it, you could think of it as an energy density too, because of course there's an energy mass relationship. This particular term is the density of dark energy in our universe. However, for this particular question that we're dealing with right now, let's see. I'm taking a quick moment to just quickly look at the comments. Astro, that is a great question. So how do we decide the variables that we're using? I have no idea why they use lambda for dark energy. I honestly don't know. I really don't know. Like for example, why did they use for the neutrinos the nu, which might be like the Greek letter N for neutrino, maybe that might make a little more sense to me. But why they use, for example, like gamma for a photon, I have no idea. But that's a really good question though. And if I ever like find out and I'm just on here, I'll let you guys know. Ha. So Larry, you have a very good question there. And that's gonna be a part of our discussion once we're done with the problem. Um, that's a very good point. So if the nutrient, basically what Larry's getting at here is you kind of brought it up earlier, but what Larry's getting at here is if the neutrinos are able to the neutrinos alone are able to yield the critical density, then that would basically mean that every other term um, it becomes unimportant. And we'll talk a little bit more about that in a second. But man, you brought it up very early actually, but it's cool. Great question. But with this problem, we're basically assuming, um, in so many words, we're assuming that our universe is simply composed of neutrinos. Basically, all the other terms are going to go to zero. That is, all the other omega terms are going to go to zero. So the idea, like basically what Larry brought up here and what I just said, was that all the other terms basically go to zero, and we're basically going to assume that the universe is composed of neutrinos, and that those neutrinos make up the critical density. And it leads basically down this line of argument that I'm presenting here, that omega, the total density of our universe, um, or the total density parameter of our universe, will end up equaling simply the density parameter for the neutrinos, which is the ratio of the mass density of neutrinos to the critical density. Now, for this to be true, we need for omega, the total density parameter, to equal 1, which, if you guys kind of remember from our last discussion, that on a total density parameter value of 1 corresponds to a flat universe. Um, so so mathematically this has to be the case, and also as far as geometry is concerned, this would correspond to a flat universe. So we have that our neutrino density is going to be equal to our critical density. And to be able to move on from there, though, we need to break down what the mass density is, in more basic terms. Of course, the ultimate idea here is to be able to. And the thing about it, and the reason why, so I'm looking over at the comment here that Larry puts. Ooh, save some for baryons. So the reason why I started off with this portion of the equation is because of the fact that you can play around with these parameters to be able to get different calculations for the neutrino rest mass. So if I wanted to, going down to the equation is kind of here in the very center of the page. Let's see if I can highlight it. And if you guys can see me highlighting stuff. Yeah, you can see it. Perfect. So going to this particular portion of the equation, or of my argument here, if I were to say that I also wanted to be able to say that baryonic matter was important in this calculation, I would add it here as another term in the center. And of course, it would also affect the far right-hand side of the equation, where we now have a density term for the baryons, if I were to say baryons were important in the total density parameter. But in this situation, we're just assuming everything else just goes away, and we're only concerned with neutrinos. And so, hey, Uncle Bill. Yes, baryons are my favorite too. Thanks to those particular, forms of matter, we're here. Um, it could be very different. This universe could be primarily composed of neutrinos. That's a possibility. Um, so right, so we're basically going to be equating our neutrino density to the critical density, and so I take into consideration that and when I was initially doing this problem, I realized, like, well, there's different types of neutrinos. So exactly how will this work out? Well, the way in which I continued my argument was that I would assume an average rest mass for the neutrinos, which denoted here as the m bar sub nu, and I would basically multiply that times the number density of neutrinos, which is the n sub nu. So making this substitution into our equation, we end up basically getting that we can now solve for this average rest mass. So the initial question, of course, asks for us to solve for the rest mass of a neutrino. But in this situation, there's different types of neutrinos, and they don't all necessarily have to have the same rest mass. So using this average rest mass variable, we're able to, at the very least, calculate an average rest mass. So taking the number density that I said that we assume, but basically I found this online. Taking the number density for neutrinos that I found online and dividing that into the critical density value. Again, all the information I'm presenting here, you can actually just find it. You can type it into Google, and like these numbers will pop up. Well, for the neutrino rest mass, or for the neutrino density, it'll be slightly different. I think it's like 330. million neutrinos per cubic meter. But that's the exact I think that's more or less close to the value that it should be, 0.3 times 10 to the 9 um, neutrinos per cubic meter. But yeah, basically just plug and chug these values in, and you're at the very least able to get an average rest mass for the neutrinos. Now, going back to what Larry stated earlier, so if neutrinos basically, if the neutrino rest mass alone could be able to produce the critical density, well, if you were to now start adding in those other terms that we kind of took out earlier, that is the density parameter for dark matter, for dark energy, for baryonic matter, and you were to utilize the values that we've calculated for those things today, along with the calculated value that we have here in this document, well, this would put us in a closed universe. So basically, what I'm getting at is this: if the average rest mass of neutrinos were equal to what I'm showing here in in the document that we see here before us, and we were to take that into consideration with all the other mass that's in the universe, as well as other things that aren't actually physically mass but affect the mass density of our universe. Oh, again, I keep doing that. I'm sorry. I have to stop that. Um, if they were to affect, or basically if the average rest mass of neutrinos were equal to this value, we'd basically be in a closed universe. This particular type of rest mass would push our total mass to being greater than the critical density, which would ultimately put our geometry as a closed universe. Oh, J. The J represents joules. So I started off in units of well, basically my density for the critical density was in units. Everything's in SI initially, and I converted to units of EV, which I can't think if that's in. I can't remember what unit system EV is a part of, but EV is a unit of energy. But given that my critical density was in SI units and it has units of kilograms, I have to be able to convert from kilograms to the different units, because whenever you're looking at the rest masses of particles, they're typically in units of eV per c squared. So the thing about that is this. That's a great question, Larry. This average, in fact, I probably can even modify the PDF document. This average neutrino rest mass doesn't really take into consideration the species of neutrino. I'm just simply saying that if the neutrino's rest mass is 18.6 eV per c squared, independent of the type of neutrino, then we get into a situation of, well, assuming of course that our universe is simply composed of neutrinos, then this would need to be the average neutrino rest mass for us to achieve the critical density, or to have a flat universe if the universe is only composed of neutrinos. But if we were to take the more realistic case where the universe is not just simply composed of neutrinos, and we also have dark matter, dark energy, baryons, photons, then a neutrino rest mass of this amount would push us into being into a closed universe, which kind of contradicts what current measurements are showing, and that is that our universe is actually more closer to being a flat universe versus a closed universe. But you can do a little bit more math tricks to this to be able to get kind of like a sum, to represent this as a sum of the rest masses of the neutrinos. Um, I probably can try to quickly add that. But basically, another way of putting this is that this average rest mass term is equivalent to 1/3. I think it's 1/3 times, or maybe it's 1/6. So the reason why I'm saying 1/6 is because I might have to also take into consideration the antimatter counterparts for the neutrinos, because they too also have mass, but their densities aren't the same though. I don't think their densities can't be the same. So maybe the situation is 1/3 times basically the sum of the masses of the neutrinos. Yeah, I think it's 1/3 times the sum of the masses of the neutrinos. And me saying that is probably not as good as me actually like physically writing it out. And I want to write it out, but I would have to open up some other software and to make the changes because everything's written in tech. And right now I'm just showing the PDF of it. But other three different types of neutrinos, those being the electron neutrino, as Larry points out, the tau neutrino, and the muon neutrino. I'm not too sure which one of those is the most massive. Is it the Does anyone know this answer by any chance? It might be the electron neutrino, given Larry's assumption. I'm myself. I'm assuming that the electron neutrino is probably the tau neutrino. So the tauon is heavier than the electron. I think that would probably have to be the case. See, guys, one of the reasons why I love our conversations is because all of these things I end up forgetting over time. And the reason why I forget is because I don't get to talk about it enough. And our conversations give me a chance to be able to have some really fun conversations about science. But guys, for the most part, that was pretty much what I wanted to discuss. This particular calculation. Okay, so the electron is the lightest. Then we have the muon, then the tauon. Okay, or the tau particle. Well, guys, if you guys have any questions, by all means, go ahead and put it into the chat, and I'll be more than happy to attempt to answer. But for the most part, that's pretty much the end of my discussion for today. And also, I do want to say this. Thank you guys for sticking around. We were having some technical difficulties earlier today, um, and you guys are all still here. Oh, no problems, Phoenix. Thanks, Astro. With this alternate universe, huh? So would the alternate universe have antineutrinos? I would have to say, I mean, yeah, I would think it would have antineutrinos. Yeah, it would have antineutrinos because even today, I mean, with our current universe, the um the number of matter of ordinary matter particles significantly outweighs the number of their antimatter counterparts. I am not going to lie. When it comes to particle physics, some of the topics can be very difficult to understand. nevertheless, it's always interesting to me. Well, in all honesty, in all honesty, even with the math that I know, it gets scary. It's still very scary to me sometimes. Some of the math I see, because I mean, I quickly came to this realization that there's a lot about math I do not know. um, Coming out of calculus 3 in undergrad, I was like, yeah, I'm good with math. I'm good. And then I really started reading some of the papers. I was like, what is this? It's I'm still learning today. So, I mean, I understand some of the more basic math concepts, but I mean, having a good understanding of the math, I think, is a necessity to be able to do really well with some of the science. But nevertheless, it's all fun to learn though, and anyone can do it if they're willing to put the time into it. So, all right, guys. Well, thank you guys for one staying and giving it having a great conversation about this topic. I will be back next Wednesday and Friday after Daily Space, and I look forward to seeing you guys then. All right, guys. Bye.